Imagine you have a magic box, not a trick box, not a toy, a truly, genuinely magic box, one that can create anything you ask for. You reach inside and wish for an apple appears. You wish for a pencil and a pencil is there. You wish for something that doesn't even exist yet, something completely imaginary, and the box builds it from scratch. But here's the part that should make your brain stop for a second. This box, this magic box, does not decide what's inside it until the moment you open it. Before you look inside, everything is in there at once. The apple, the pencil, the imaginary thing, every single possibility, all existing together in the same space at the same time. And the instant you lift the lid, the very instant your eyes make contact with the inside of the box, only then does the box make up its mind. Only then does one thing become real and everything else vanish. Now I know what you're thinking. That sounds like a fairy tale. That sounds like the kind of thing someone made up to sound deep at 3 in the morning. But here's what I need you to understand before we go any further. That is not a metaphor. That is not a philosophical thought experiment invented to sound clever. That is literally, precisely, demonstrably how the smallest pieces of our universe actually work. A particle, a real physical particle, the kind that makes up your body, your phone, the chair you're sitting on. That particle, when no one is looking at it, when no measurement is being made, does not have a single definite position. It does not have a single definite state. It exists in every possible configuration simultaneously, like a ghost version of all its possible selves, smeared across space. And the moment someone looks at it, the moment it gets measured, touched, interacted with in any way, all of those possibilities collapse into one, just one, and the rest disappear. This is not science fiction. This is not fringe theory. This is quantum mechanics, the most precisely tested, most experimentally verified scientific framework in the history of human civilization. And what it tells us about the nature of reality is so strange, so deeply unsettling, that it kept the greatest minds of the 20th century awake at night. Albert Einstein, one of the 2 or 3 most brilliant human beings to ever walk this planet, was so disturbed by the implications of quantum mechanics that he spent the last 30 years of his life trying to prove it wrong. He couldn't. He died still arguing. And then, in 2022, 3 scientists won the Nobel Prize in physics. Not for discovering something new, not for building a faster computer or finding a new particle. They won it for settling a 100-year-old argument about the fundamental nature of reality itself. For proving, through experiment, that reality is not what we always thought it was. They proved that things do not necessarily exist in a definite state when no one is looking at them. They proved that the universe, at its deepest level, is not made of solid, fixed, independent things, but of something far stranger, far more interconnected, far more slippery than anything our everyday intuition can grasp. So today, we are going to open that magic box. We're going to go as deep as physics currently allows us to go, into the fabric of what exists, and we are going to come face to face with a question that does not have a comfortable answer. What is reality, actually? And does it exist when no one is looking? Let's go. What is everything made of? Before we can understand why reality might not be real, we first need to understand what reality is supposed to be made of. Because to understand why quantum mechanics is so strange, we first need to understand what we thought before quantum mechanics came along and destroyed everything. The question of what everything is made of is not a new one. Humans have been asking it for thousands of years. You can find it in ancient Greek philosophy, in Indian Vedic texts, in Chinese natural philosophy. Across every civilization that ever existed, at some point someone sat down and asked, if I take something and break it into smaller and smaller pieces, what do I eventually end up with? What is the most basic building block? What is the final, irreducible thing? The ancient Greeks had their own answer. Some of them thought that everything was made of 4 fundamental elements: fire, water, earth, and air. And by our modern standards, that sounds almost laughably wrong. But actually, as an idea, it was revolutionary. Because for the first time, it was saying, all of this complexity, all of these wildly different things in the world, might reduce down to just a small number of simple ingredients. That's a profound conceptual leap. That's the seed of reductionist science. Then, a little over 2,000 years later, science started to catch up with that instinct. In the 18th and 19th centuries, chemistry began identifying what we now call elements, substances that couldn't be broken down into simpler things by chemical means. Hydrogen, oxygen, carbon, iron, gold. Each one distinct, each one with its own behaviour. And by the late 1800s, scientists had mapped out over 60 of these elements and organised them into the periodic table. But here's the thing, that still wasn't the bottom level. Because then came the atom. The word atom comes from the Greek word atomos, which means indivisible. The idea was simple. If you kept cutting something smaller and smaller, eventually you'd reach a point where you couldn't cut anymore. A particle so small it had no internal structure, no parts, nothing to break it down further. The atom was supposed to be that particle, the final frontier, the ultimate Lego brick. And for a while, right around the turn of the 20th century, scientists genuinely believed they'd found it. The atom was the answer. Everything was made of atoms. Case closed. Except it wasn't closed. Because then, in a series of experiments that started in the 1890s and continued into the early decades of the 20th century, scientists started to discover that the atom itself had parts. First came the electron, a tiny negatively charged particle discovered by J.J. Thomson in 1897. Then came the discovery that atoms have a nucleus, a dense, positively charged core at their centre, identified through Ernest Rutherford's famous gold foil experiment in 1909. And then it turned out the nucleus itself was made of things, protons and neutrons. And then, in the 1960s and 70s, physicists discovered that even protons and neutrons are not fundamental. They're made of even smaller particles called quarks, held together by particles called gluons. So here's where we ended up, after a century of peeling back layers. At the centre of every atom, there's a nucleus packed with protons and neutrons. Surrounding that nucleus, there are electrons. And inside those protons and neutrons, there are quarks. Electrons and quarks appear to be fundamental. As far as we can tell, they have no internal parts, no smaller components. They're as basic as it gets. Now here's something extraordinary. Consider this. Every single thing you can see, touch, taste, or smell in this entire universe is made from combinations of roughly 90 naturally occurring elements. And those 90 elements are all made from the same three building blocks: protons, neutrons, and electrons. And the thing that determines which element an atom is simply the number of protons in its nucleus. That's it. That one number determines everything. If an atom has one proton, it's hydrogen, the lightest element, the most abundant thing in the universe. If it has 6 protons, it's carbon, the backbone of all organic chemistry, the foundation of all life. If it has 79 protons, it's gold. If it has 78, it's platinum, a completely different metal with completely different properties. 1 proton. That's all the difference between gold and platinum. 1 proton's difference between you and a rock is just a matter of which atoms are present and how they're arranged. The universe is doing something breathtaking here. With just a handful of basic ingredients and one simple counting rule, it's generating everything. Every metal, every gas, every living thing, every colour, every texture, every substance that has ever existed. And all of this, all of this overwhelming complexity is just the surface level, because when scientists started looking not just at what particles were, but at how they behaved, at what they actually did when no one was looking, that's when everything fell apart. That's when they discovered that the rules governing the very small were nothing like the rules governing the very large. That the subatomic world operates by a completely different logic, one that doesn't care about our intuitions, doesn't respect our assumptions, and doesn't behave anything like the solid, predictable, common-sense world we think we live in. That's when quantum mechanics arrived, and nothing was ever the same again. To really feel the shock of quantum mechanics, you need to understand what scientists believed before it, because the picture they had was so elegant, so satisfying, so utterly convincing that it felt like the final word on how the universe worked. It's called classical mechanics, or Newtonian physics, named after Isaac Newton, who formulated its core principles in the 17th century. And the basic idea is this: the universe is like an enormous clock. Everything in it moves according to fixed, deterministic laws. If you know the position and speed of every particle in the universe at this moment, you can, in principle, calculate exactly what every particle will be doing at any point in the future. And you can run it backward to know exactly what every particle was doing at any point in the past. Cause and effect, action and reaction, predictability, certainty. That was the promise of classical mechanics, and it worked incredibly well. Newton's laws predicted the motion of planets with stunning accuracy. They explained the trajectory of cannonballs and the swing of pendulums. By the 19th century, the French mathematician Pierre-Simon Laplace had articulated the vision in its most extreme form. He imagined an intellect, an omniscient demon that knew the position and speed of every particle in the universe. He wrote that for such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes. The universe in this picture is deterministic. Everything that happens had to happen. Everything that will happen must happen. The future is already written. We just don't have the ability to read it yet because we don't have access to all the information. This was the world that scientists believed they lived in as the 19th century drew to a close. A world of solid, definite things. A world governed by precise, knowable laws. A world where uncertainty was just ignorance, not a fundamental feature of reality itself. And then quantum mechanics arrived and demolished all of it. It didn't happen all at once. It was gradual, almost reluctant. Scientists in the late 19th and early 20th centuries started noticing that certain phenomena, things like the way hot objects glow, the way light interacts with metal to knock out electrons, the way atoms emit light in distinct colors, couldn't be explained by classical physics. No matter how hard they tried, the math didn't work. The predictions didn't match the experiments. The first crack appeared in 1900, when a German physicist named Max Planck was trying to explain the spectrum of light emitted by hot objects. He found that the only way to make the math work was to assume that energy doesn't flow continuously, like water, but comes in discrete chunks, like coins. He called these chunks quanta. He didn't fully believe his own idea. He thought it was a mathematical trick, a shortcut that happened to give the right answer. He didn't realize he'd just started a revolution. 5 years later, Albert Einstein took Planck's idea and ran with it. He used it to explain the photoelectric effect, the phenomenon where light hitting metal knocks out electrons. Einstein proposed that light itself comes in discrete chunks of energy, particles of light, which we now call photons. This was radical. The wave nature of light had been established for nearly a century, and now Einstein was saying it was also a particle? That contradiction, the same thing being both a wave and a particle, would turn out to be one of the defining puzzles of quantum mechanics. And it was only the beginning. Over the next 2 decades, scientists like Niels Bohr, Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and Max Born assembled the full framework of quantum mechanics. And what emerged from that effort was something that should not work, something that should not be true, something so weird that even the people who built it struggled to accept it. The universe, it turned out, was not a clockwork machine. It was not deterministic. It was not predictable in principle. At the deepest level, reality itself was fuzzy, uncertain, probabilistic, and worst of all, it seemed to depend on being observed. Let's get to the heart of it. The thing that makes quantum mechanics so strange, so counterintuitive, so genuinely world-altering. And it starts with a concept called superposition. In classical physics, a particle has a definite position at every moment. It's here or it's there. It's moving left or it's moving right. It's spinning up or it's spinning down. It has properties, and those properties have definite values, and you could, in principle, measure them all precisely at the same time. Quantum mechanics says, no, not even close. In the quantum world, a particle does not have definite properties before they're measured. Instead, it exists in a superposition, a simultaneous combination of all the possible states it could be in. It's not just that we don't know which state it's in. It's that the state itself is genuinely undefined, genuinely indeterminate, genuinely not yet decided. This is such a radical claim that it needs an analogy. So let's go back to the magic box. Before you open it, the box contains everything. Apple, pencil, everything. All the possibilities coexist. Now imagine that this isn't just about what you find when you look. It's about what actually physically exists before you look. Before you open the box, there is no apple and no pencil. There is just a kind of shimmering probability cloud that contains the potential for apple and the potential for pencil, neither of which has physically crystallized into existence yet. That's superposition. The particle isn't hiding somewhere, and we just don't know where. It literally has no definite location. It has no definite spin. It exists as a spread of probabilities, a mathematical ghost of all its possible selves, until the moment of measurement. Now, scientists represent this mathematically using something called the wave function. The wave function is essentially a probability map of a particle. It doesn't tell you where the particle is. It tells you the probability of finding the particle in each possible location if you were to measure it. When no measurement is happening, the particle's wave function spreads out across space. It's simultaneously everywhere it could be, with different probabilities attached to different places. This spreading isn't just conceptual, it has real physical consequences. There's a famous experiment called the double slit experiment that demonstrates it directly, and it's one of the most haunting things in all of physics. Here's the setup. You take a barrier with 2 narrow slits cut into it. You fire particles, electrons say, at the barrier one by one. On the other side, you have a detector screen that records where each electron lands. Now, in classical physics, if you fire particles at 2 slits, you'd expect to see 2 piles of impacts on the screen, one behind each slit. That's what little balls would do. They'd go through one slit or the other and pile up accordingly. But that's not what happens. When you fire electrons at the double slit without watching which slit they go through, you get an interference pattern on the screen. A series of alternating bands, light and dark stripes, the same pattern you'd get if you were sending waves through 2 slits instead of particles. The pattern that forms only when 2 waves overlap and interfere with each other. But here's the thing. You're firing single electrons, one at a time. There's only one electron in flight at any given moment. How can a single electron interfere with itself? The only way to explain the interference pattern is to say that the electron went through both slits simultaneously, that it existed in a superposition of two paths at the same time. And it gets even stranger. If you set up a detector to watch which slit each electron goes through, if you gather that information, the interference pattern disappears. Suddenly, you get the classical result: two piles, as if the electrons reverted to being ordinary particles the moment you started observing them. The act of observation, of gaining information about which path the electron took, changes the outcome of the experiment. The electrons know they're being watched. I want you to sit with that for a moment, because it's genuinely shocking. We're not talking about a subtle statistical effect. We're not talking about the measuring instrument disturbing the electron in some mechanical way. We're talking about a fundamental change in the behavior of reality depending on whether information is acquired or not. The universe behaves differently based on whether knowledge is extracted from it. This is what the wave function is describing. Before measurement, the wave function spreads out. The particle takes all paths. The quantum state is a superposition. After measurement, the wave function collapses. All the probability concentrates into one outcome, and the particle appears in one definite place. This collapse is called wave function collapse, and it is one of the deepest mysteries in all of physics, because no one, even now, fully agrees on what it actually is. What causes it? What does it mean? Is it a physical process? Is it just a mathematical bookkeeping update? Does the universe literally branch into multiple copies? These are questions we will get to, but first let's talk about a famous thought experiment that took this weirdness and turned it into something even more disturbing, by dragging it out of the quantum world and dropping it into our everyday world, by asking, what if a cat were in superposition? The year is 1935. Quantum mechanics has been around for about a decade in its modern form. The equations work brilliantly. They predict experimental results with extraordinary precision. But what quantum mechanics actually means, what it's saying about reality, is deeply contested. At the center of the debate is the Copenhagen interpretation, the official position of most quantum physicists at the time, associated most closely with the Danish physicist Niels Bohr. The Copenhagen interpretation says, essentially, a quantum system does not have definite properties before measurement. The wave function represents a genuine superposition of all possible states, and when a measurement is made, the wave function collapses to a definite outcome. An Austrian physicist named Erwin Schrödinger found this deeply unsatisfying. He'd actually been one of the architects of quantum mechanics. He formulated the famous Schrödinger equation, which describes how the wave function evolves over time. But he thought the Copenhagen interpretation was either incomplete or absurd. He wanted to show why, so he invented a thought experiment. Not a real experiment. You don't actually do this. It's a mental exercise designed to expose the implications of taking quantum mechanics at face value. Here's the setup. You take a box, a perfectly sealed, perfectly isolated box. Inside the box, you put a cat. You also put a tiny piece of radioactive material, a radiation detector, a vial of poison, and a hammer positioned above the vial. The radioactive material is quantum mechanical. Its decay is governed by quantum probability. Over the course of 1 hour, there is exactly a 50% chance that it will emit a particle and a 50% chance that it won't. The machine is rigged so that if the detector registers a particle, if the radioactive material decays, the hammer falls, the vial breaks, the poison is released, and the cat dies. If no particle is detected, the hammer doesn't fall, the vial stays intact, and the cat lives. Now leave the box sealed for 1 hour. Don't look, don't measure, don't interact with it in any way. According to quantum mechanics, before the box is opened, the radioactive material is in a superposition. It has both decayed and not decayed simultaneously. And since the cat's fate is directly tied to the quantum state of the radioactive material, the cat must also be in a superposition. The cat is simultaneously alive and dead. Not alive and we don't know it. Not dead and we don't know it. Genuinely, physically, actually both alive and dead at the same time in quantum superposition until the box is opened and a measurement is made, at which point the wave function collapses. The cat is either alive or it's dead. The superposition resolves. Now, Schrödinger's intention was not to say, "Look how cool quantum mechanics is." His intention was to say, "Look how ridiculous this is." He was highlighting what he saw as an absurdity in the Copenhagen interpretation. A cat cannot be both alive and dead. That's not how the macroscopic world works. So if quantum mechanics predicts that, then something must be wrong with quantum mechanics, or at least with our interpretation of it. But here's the twist. The physics community did not react by abandoning quantum mechanics. They reacted by taking the cat seriously, or rather, by taking the puzzle seriously. Because the experiment exposes a genuine and unresolved question that is still at the frontier of physics today. Where is the boundary? Where does the quantum world end and the classical world begin? Why does superposition seem to apply to electrons and photons, but not to cats and chairs? At what scale does the fuzzy quantum behavior give way to the solid, definite, classical behavior we observe in everyday life? This question is called the measurement problem, and it doesn't have a universally agreed upon answer. Different interpretations of quantum mechanics give different answers, and we will get to those. But for now, keep the cat in mind, because it's going to come back. What Schrödinger's cat really showed us is this. The weirdness of quantum mechanics isn't confined to the tiny world of particles. The quantum and the classical are not separate domains with a clean border between them. The quantum world bleeds upward. The superposition of a radioactive nucleus, in principle, entangles itself with everything it interacts with: the detector, the hammer, the vial, the poison, the cat, the air in the box. In principle, everything inside that box is in superposition. The reason we don't see superposition in everyday life isn't because superposition doesn't apply. It's because the moment a quantum system interacts with a large number of particles in the environment, with air molecules, with photons bouncing around, it rapidly gets entangled with all of them. Its quantum behavior becomes scrambled across trillions of particles in such a way that we can't observe it anymore. This process is called decoherence. But here's the thing. Decoherence doesn't actually solve the measurement problem. It doesn't tell you why you see one outcome rather than another. It doesn't explain where the other branches go. It just explains why superposition becomes undetectable at the macro scale. The deep mystery, what actually happens when a measurement is made and why, remains. And that mystery is precisely what makes quantum mechanics so philosophically explosive. So let's go deeper. Before we get to the really mind-bending stuff, entanglement, the Nobel Prize, the nature of reality, there's one more piece of the foundation we need to build. Because we've been talking about particles as if they're tiny little balls, little specks of matter flying around in space. And that picture, while useful as a starting point, is not actually what quantum physics says reality is made of. The deepest version of quantum mechanics, quantum field theory, tells a very different story. In quantum field theory, the fundamental thing is not the particle. The fundamental thing is the field. A field in physics is something that has a value at every single point in space. The temperature in a room is a field. Every point in the room has a temperature. The gravitational field of the Earth assigns a gravitational strength and direction to every point in space around it. Fields are everywhere. Fields fill everything. Now, quantum field theory says that the fundamental constituents of reality are not particles. They're quantum fields. There is an electron field that permeates all of space and time. There is a photon field, more properly called the electromagnetic field, that permeates all of space and time. There is a quark field, a Higgs field. For every type of fundamental particle we know about, there is a corresponding quantum field that fills the entire universe. And what is a particle? A particle is a localized disturbance in one of these fields, a ripple, an excitation, a vibration. Think about the surface of a lake. The water is the field. When you throw a stone in, you create a ripple, a wave that travels across the surface. That ripple isn't a separate thing from the water. It's a disturbance in the water. It's the water doing something at that particular place. A particle is like that ripple. An electron isn't a tiny ball of stuff floating in space. It's a ripple in the electron field. A photon isn't a little pellet of light. It's a ripple in the electromagnetic field. These fields are real. They're physical. They fill the universe. And particles are just the way these fields manifest when energy gets concentrated in one place. This picture has some deeply strange implications. First implication: empty space is not empty, not even close. Every quantum field permeates all of space, and quantum mechanics says these fields are never perfectly still. They're always fluctuating, always vibrating with a minimum baseline amount of energy called the zero-point energy. These fluctuations can spontaneously create pairs of particles, a particle and its antiparticle, that pop into existence for a tiny fraction of a second and then annihilate each other. These are called virtual particles, and they're not science fiction. They have measurable effects. The Casimir effect, a tiny attractive force between two uncharged metal plates placed very close together, is caused by virtual particles. The tiny shift in the energy levels of hydrogen atoms, called the Lamb shift, is caused by virtual particles. We can measure these effects. They're real. So the vacuum of space, what we call empty space, is actually a seething, churning, roiling sea of quantum fluctuations, with particles constantly blinking in and out of existence. Empty space is not empty. It is the most fundamental, most energetically active thing that exists. Second implication: you can never truly isolate a particle and look at it as it really is, independent of everything else. When you measure a particle, you're not passively observing something that's sitting still waiting for you. You're interacting with a quantum field. The act of measurement involves a transfer of energy that disturbs the field. The thing you're measuring and the measuring apparatus are not separate. They become entangled with each other during the measurement process. Third implication: identity becomes blurry. In classical physics, if you have two identical billiard balls, you can still tell them apart. Ball number 1 is the one on the left. Ball number 2 is the one on the right. But in quantum field theory, two electrons are not just identical in the way that two billiard balls with the same mass and color might be identical. They are genuinely indistinguishable, not just practically, but in principle. There is no fact of the matter about which electron is which. They're not really individual things. They're excitations of the same underlying field, and the field doesn't care about identity. This is the true picture that quantum field theory paints, not a universe made of tiny balls bouncing around in empty space. A universe made of invisible, all-pervasive fields, constantly fluctuating, never quiet, with particles as temporary disturbances, ripples in the fabric of those fields. And this fabric, these fields, are what gets put into superposition, what gets entangled, what collapses. Understanding this makes the next part hit even harder, because now we need to talk about a principle that even this field picture can't get around. A principle that places an absolute non-negotiable limit on what can be known about the universe, not because of our ignorance, but because of the nature of reality itself. In 1927, a 25-year-old German physicist named Werner Heisenberg wrote down a short equation that changed our understanding of the universe forever. It's called the Heisenberg uncertainty principle, and it is one of the most profound, most counterintuitive, most philosophically explosive statements in the history of science. Here it is in plain English. You cannot simultaneously know, with perfect precision, both the position and the momentum of a particle. The more precisely you pin down where a particle is, the less precisely you can know how fast it's moving and in which direction. And the more precisely you know its momentum, the less precisely you can know its position. There is an irreducible, fundamental, unavoidable fuzziness built into reality itself. Now, the first reaction most people have to this is, that's just a practical limitation. That's just saying that our measuring instruments disturb the particle. If I try to see where an electron is, I have to hit it with a photon, and that photon kicks the electron and changes its momentum. So of course I can't measure both perfectly, my measurement interferes with the system. That explanation is wrong, or at least drastically incomplete. The uncertainty principle is not about the disturbance caused by measurement. It is not about the limits of our instruments. It is not about our ignorance. It is a statement about what exists in reality before any measurement is made. The position and momentum of a particle are not jointly well defined before you measure them. The particle does not have a precise position and a precise momentum that are waiting to be discovered. It has a probability distribution over positions and a probability distribution over momenta. And these two distributions are linked by a mathematical relationship. They are Fourier transforms of each other, such that making one narrow inevitably makes the other wide. Here's an analogy that helps. Think about a musical note. A pure single musical tone has a precise frequency. It's vibrating at exactly, say, 440 Hz. But a pure tone also goes on forever. It has no definite time. If you want a sound that exists at a precise moment in time, a very short, sharp click, you need to combine many different frequencies together. The more time-localized the sound is, the more spread out it is in frequency space. And vice versa, the more precisely defined the frequency is, the more the sound has to be spread out in time. Position and momentum in quantum mechanics are related in exactly the same way. It's not just that we can't know both at once. It's that a particle in a state of very precise position literally has no definite momentum. Its momentum is genuinely, physically, spread out over a range of values. And a particle with very precise momentum literally has no definite position. Its position is genuinely, physically smeared over a large region of space. This is baked into what particles are. It's not a limitation of our knowledge. It's a feature of reality. Einstein hated this, deeply, personally hated it. His famous declaration, "God does not play dice," was directed at exactly this principle. He believed that the universe had a definite, deterministic underlying structure, and that quantum mechanics was simply incomplete, that there were hidden variables, hidden facts about each particle, that quantum mechanics wasn't capturing, but that a future, better theory would reveal. In that world, particles would have definite positions and momenta all along. We just couldn't see them. The uncertainty wouldn't be in reality, it would be in our knowledge of reality. This argument, that quantum mechanics must be hiding some deeper, deterministic layer beneath the probability, was not a fringe view. It was Einstein's view. and Einstein was not an easy man to dismiss. So the question became, was quantum mechanics fundamentally incomplete, with hidden variables waiting to be discovered? Or was the uncertainty, the probability, the non-definiteness, was all of that real? Was the universe genuinely, fundamentally, irreducibly probabilistic? For decades, this was purely philosophical. There seemed to be no experiment that could settle it. Both views predicted the same outcomes. You couldn't tell them apart by measuring anything. And then someone figured out how to test it. And the answer turned out to be one of the most shocking things science has ever discovered. In 1935, the same year Schrödinger published his cat thought experiment, Einstein co-authored a paper with two colleagues, Boris Podolsky and Nathan Rosen, that would become one of the most important and most debated papers in the history of physics. It's known as the EPR paper, after the initials of its authors, and its purpose was to prove that quantum mechanics was incomplete. The argument goes like this. Quantum mechanics says that particles don't have definite properties before measurement, but what if you have two particles that are entangled, linked together in a quantum state that correlates their properties? Here's what entanglement means. When two particles interact in certain ways, they can become quantum mechanically linked. Their wave functions merge into a single joint wave function that describes both particles together. And this joint state can have a very specific structure. The properties of the two particles are correlated, but neither particle has a definite value of those properties on its own. For example, take two particles and entangle their spins so that their total spin is zero. Neither particle has a definite spin on its own. Each is in a superposition of spin up and spin down. But they're correlated such that if one is measured and found to be spin up, the other must be spin down. And if one is found to be spin down, the other must be spin up. Now, and this is the key, separate the two particles. Send them to opposite ends of the galaxy, light years apart, so far that no signal travelling at the speed of light could get from one to the other in the time it takes to do the experiment. Now measure particle A. It randomly collapses to spin up. Instantaneously, particle B, on the other side of the galaxy, becomes spin down. Not after a delay, not after a signal travels from A to B. Instantly. Einstein's argument was, this cannot be right. Nothing travels faster than light. If measuring particle A instantly determines the state of particle B, that means either some signal travelled faster than light, which Einstein's own special relativity says is impossible, or the information was already there. The spin of both particles was already determined before any measurement was made. Quantum mechanics just wasn't tracking that hidden fact. Einstein called the alternative genuine instant correlation across any distance. Spooky action at a distance. He meant it dismissively. It sounded ridiculous. It violated his deepest convictions about locality, the idea that things can only be directly affected by things in their immediate surroundings, not by things far away. His conclusion: quantum mechanics must be incomplete. There must be hidden variables, some deeper layer of information not captured by the wave function that determines the outcomes of measurements in advance. For 2 decades, this was untestable. The EPR paper was brilliant, but it didn't offer a way to distinguish between quantum mechanics is right about instant correlations and hidden variables are real and the correlations were always in there. Both theories made the same predictions. Then came John Bell. In 1964, the Irish physicist John Stuart Bell published a theorem, now called Bell's theorem, that did something extraordinary. He showed that quantum mechanics and hidden variable theories don't always make the same predictions. There are specific experimental situations where they diverge, where the correlations between entangled particles are stronger mathematically than any hidden variable theory could possibly produce. He derived a mathematical inequality, Bell's inequality, that any hidden variable theory must satisfy. If the correlations measured in real experiments violated Bell's inequality, it would prove that hidden variables couldn't be the explanation. It would prove that Einstein was wrong. The inequality could be tested, and so the experiments began. The first serious experimental test was conducted in 1972 by John Clauser at Berkeley, working with Stuart Friedman. They created pairs of entangled photons and measured the correlations between them at different angles. The results violated Bell's inequality. The correlations were stronger than any local hidden variable theory could explain. But the experiments had loopholes. Maybe the photons somehow communicated with each other through the detectors. Maybe there was some other classical explanation that hadn't been considered. The results were suggestive but not conclusive. Then in the early 1980s, the French physicist Alain Aspect ran a series of much more refined experiments. He used a clever setup that could switch the measurement angles after the photons had already been emitted, closing the main loophole. He used technology that allowed him to ensure no signal could travel from one detector to the other in the time it took to make the measurement. His results also violated Bell's inequality. Significantly, unambiguously. And then Anton Zeilinger and his team in Vienna took it even further. Over the decades that followed, Zeilinger and his collaborators pushed the experiments to greater and greater precision, closing more and more loopholes, testing more and more extreme versions of entanglement. His group demonstrated entanglement over distances of tens of kilometers. They showed that the correlations persisted regardless of distance and regardless of how fast the measurement settings were changed. Every single experiment told the same story. Bell's inequality is violated. Hidden variables don't work. The correlations are real. The spooky action at a distance that Einstein found so repugnant, it's real. In 2022, the Nobel Committee in Physics awarded the Nobel Prize to John Clauser, Alain Aspect, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Think about what that means. The Nobel Prize, the most prestigious scientific award in the world, was given for proving that Einstein was wrong, for proving that reality is not locally real, for proving that particles don't have definite properties hidden inside them before measurement, and that measuring one particle can instantly correlate with the result of measuring another particle, regardless of how far apart they are. This is not a subtle result. This is not a matter of interpretation. This is something that has been experimentally demonstrated, verified, and re-verified in dozens of independent experiments around the world. The Nobel Prize is the global scientific community saying, "This is settled. This is how the universe works." Local realism, the idea that things have definite properties when unobserved, and that distant things can't instantly affect each other, is false. And now the question is, if local realism is false, what is true? If particles don't have hidden properties, and if distant particles can be instantly correlated, what does that say about the nature of reality? This is where the interpretations of quantum mechanics come in, and they are deeply, wonderfully, disturbingly strange. Remember the wave function collapse? When you measure a particle, the wave function, which had been spread out over all possible states, suddenly collapses to one definite outcome. The Copenhagen interpretation says, this collapse is real. It happens. You get one result, and the other possibilities vanish. But there's a problem. The Schrödinger equation, the equation that describes how wave functions evolve over time, never produces collapse. The Schrödinger equation is deterministic. It says, given the wave function at this moment, Here is exactly what it will look like at the next moment, and its evolution is smooth, continuous, reversible. It does not produce sudden collapses. It does not select one outcome and eliminate the others. So where does collapse come from if the Schrödinger equation is the fundamental law governing quantum evolution and the Schrödinger equation doesn't produce collapse? Then collapse is either an additional process that needs to be added to the theory, one that kicks in during measurement but not otherwise, or collapse doesn't actually happen at all. That second option, collapse doesn't happen, is the starting point for one of the most radical interpretations of quantum mechanics ever proposed. In 1957, a young Princeton graduate student named Hugh Everett III wrote his doctoral thesis proposing exactly this. The wave function, Everett said, never collapses. Ever. The Schrödinger equation always holds. Always. Every possible outcome of every quantum measurement actually happens, but in different branches of a universal wave function. When you measure a particle that's in a superposition of spin up and spin down, you don't get one result and the other vanishes. Instead, the universe, the entire universe, including you, branches into two versions. In one branch, you measure spin up. In the other branch, you measure spin down. Both of those versions of you are real. Both are conscious. Both go on to live their lives, having experienced one outcome or the other, with no memory of the branching having occurred. This is the many worlds interpretation, also called the Everett interpretation or the relative state formulation. And it is exactly as dramatic as it sounds. Every quantum event, every radioactive decay, every photon absorption, every particle interaction causes the universe to branch. All outcomes occur. All branches are real. The universe is constantly, continuously, unimaginably proliferating into an almost infinite number of parallel versions of itself. In this picture, Schrödinger's cat is not simultaneously alive and dead. It's alive in one branch and dead in another. The apparent absurdity dissolves. There's no mystery about what happens to the cat, because in one branch the cat is fine, and in another branch the cat is dead, and both of those branches are equally real. Entanglement also gets a clean explanation in many worlds. When you measure particle A and get spin-up, you're in a branch where you measured spin-up. In that same branch, particle B is spin-down, not because some signal travelled between them, but because the branch you're in was already the spin-up/spin-down branch. The correlations are just correlations within our given branch. No spooky action required. Many worlds also solves the measurement problem. There is no measurement problem. Measurement isn't a special process that triggers collapse. Measurement is just a quantum interaction. And like all quantum interactions, it causes branching. The weird, unexplained boundary between quantum and classical disappears, because there is no boundary. Everything is quantum. Everything obeys the Schrödinger equation. The classical world we observe is simply what quantum mechanics looks like from the inside of one branch. So why isn't everyone convinced? Why is many worlds controversial? Several reasons. First, it's ontologically extravagant in the extreme. It posits an unimaginable number of parallel universes, none of which can ever communicate with any other, all continuously multiplying. That's a lot to swallow. Second, and more technically troubling, is the problem of probability. Quantum mechanics assigns probabilities to outcomes. The Born rule tells you the probability of each possible measurement result based on the wave function. But in many worlds, all outcomes occur with certainty. So where do the probabilities come from? Why do we experience outcomes with the relative frequencies predicted by the Born rule? This is called the probability problem, and it's deeply contested. Some researchers believe it can be resolved using the theory of rational decision-making under branching. Others are not convinced. Third, the branches can never be detected from within any branch. There's no experiment you can do from inside your branch that would tell you whether the many worlds picture is correct or whether some other interpretation is. All interpretations make identical predictions, and this brings us to the deepest, most unsettling thing about quantum mechanics. The interpretations are underdetermined by the evidence. We can't, at least not yet, and possibly not ever, tell them apart. Here is the central maddening fact of quantum mechanics. The theory works. It is the most precisely tested theory in the history of science. Its predictions have been confirmed to more decimal places than any other theory we have. It has never, not once in a century of relentless experimental testing, made a prediction that turned out to be wrong. And yet physicists fundamentally disagree about what it means, about what it is saying about reality, about what the universe actually is. The mathematics is agreed upon. The predictions are agreed upon. The results of experiments are agreed upon. But when you ask, what is the universe actually doing when a quantum measurement is made, you get wildly different answers from different physicists. And here's the terrifying part. There is currently no experiment that can distinguish between these answers. They all predict exactly the same thing for every experiment we know how to perform. Let's walk through the main contenders. The Copenhagen interpretation, as we've discussed, says that the wave function is a complete description of a quantum system's state and that wave function collapse is real. It happens during measurement. What causes collapse? What counts as a measurement? The Copenhagen interpretation doesn't say. It deliberately avoids those questions or treats them as outside the scope of physics. Bohr famously said there is no quantum world. There is only an abstract quantum physical description. It is wrong to think the task of physics is to find out how nature is. Physics concerns what we can say about nature. This is deeply unsatisfying to many physicists. It seems to say, don't ask what's really happening. Just use the equations and get your predictions. This is sometimes disparagingly called shut up and calculate. The many worlds interpretation, as we've seen, says collapse never happens. The wave function is everything, and it always evolves according to the Schrödinger equation. Every outcome occurs in a different branch. There is only one universal wave function, constantly branching, representing all of reality. Then there's Bohmian mechanics, also called pilot wave theory. This one is closer to what Einstein wanted. It's a hidden variable theory, but it's a very specific one. In Bohmian mechanics, particles do have definite positions at all times. The position of a particle is real and definite even when unobserved. However, the particle is guided by a wave, a real physical wave described by the wave function that influences where the particle goes. The wave and the particle are both real. The wave guides the particle's trajectory, and the particle always has a definite position. This seems to give us back the classical clockwork universe that Einstein wanted. So what's the catch? The catch is non-locality. In Bohmian mechanics, the guiding wave is a wave in the configuration space of all particles simultaneously, not in ordinary three-dimensional space. The motion of any particle can be instantly influenced by what's happening to any other particle anywhere in the universe. The spooky action at a distance isn't eliminated. It's embraced, built into the foundation of the theory. Bohmian mechanics is explicitly non-local. This is the price you pay for restoring definiteness. You give up locality. Bell's theorem is not avoided. You can't have both local hidden variables and the quantum predictions. So Bohm chooses hidden variables and accepts non-locality. Then there are approaches that try to modify quantum mechanics rather than just interpret it. The GRW theory, named after its inventors Girardi, Rimini, and Weber, proposes that wave function collapse is a real physical process, but a spontaneous one. It happens randomly, not because of observation, but just because it happens. The theory modifies the Schrödinger equation to include occasional, random collapses. These collapses are so rare and so tiny that for individual particles, they're essentially undetectable. But for macroscopic objects containing trillions of particles, the collapses pile up and essentially guarantee that the object always has a definite position. This neatly explains why quantum superposition is invisible at the macro scale. The problem with GRW is that it's a modification of quantum mechanics, not just an interpretation. And so far, the modifications predict essentially the same results as standard quantum mechanics within our current experimental precision. It's not ruled out, but it's not confirmed either. And finally, there's cubism, quantum Bayesianism, which takes the most radical epistemological stance of all. Cubism says that the wave function is not a description of the physical world at all. It's a description of an agent's beliefs about what they will experience when they make a measurement. Quantum mechanics, in this view, is not a theory about objective reality. It's a tool for reasoning about outcomes of experiments. The collapse of the wave function when a measurement is made is not a physical event. It's just the agent updating their beliefs based on new information. Cubism dissolves many of the paradoxes of quantum mechanics by arguing that they arise from trying to read too much into the formalism. There is no Schrödinger's cat problem because the cat is not in a superposition. The wave function just represents our uncertainty before we look. There is no measurement problem because measurement just means an agent has an experience. The price of cubism is a retreat from objectivity. It seems to make physics fundamentally first person, about what agents experience, not about what's out there. Many physicists find this unacceptable. So here we are, 5 major interpretations: Copenhagen, many worlds, Bohmian mechanics, GRW, cubism, plus several more that we haven't even mentioned. All of them agree on every experimental prediction. All of them are consistent with everything we've ever measured. And none of them can currently be tested against each other. Some physicists find this situation fascinating. Others find it deeply alarming. Because science is supposed to give us a picture of what the universe is. And here, at the deepest layer of our understanding, we have beautiful, perfect equations, and no agreement whatsoever on what those equations are describing. This is not a new situation. It's been going on for 100 years. But it matters more now than ever, because quantum mechanics is no longer just an academic theory. It's the foundation of technologies that we use every day, and it may be the key to technologies of the future that could transform civilization. It would be easy to walk away from all this philosophical uncertainty and ask, does any of it matter? Does it matter whether the many worlds interpretation is true or whether cubism is right? If all interpretations give the same experimental predictions, isn't the whole debate just philosophy? In terms of pure scientific prediction, maybe, but in terms of technology, in terms of what we can build using our understanding of quantum mechanics, it matters enormously. Quantum mechanics isn't just a theory about the very small, it's the foundation of the modern world. The transistor, the basic building block of every computer, smartphone, and electronic device, works because of quantum mechanics. Without the quantum mechanical understanding of how electrons behave in semiconductor materials, there are no transistors. Without transistors, there is no modern computing. Without modern computing, there is essentially no modern civilization as we know it. The laser works because of quantum mechanics. MRI machines in hospitals work because of quantum mechanics. The chemical bonds that hold together every molecule in your body are quantum mechanical in nature. GPS satellites work partly because of corrections for quantum mechanical effects. The periodic table of elements, with all its predictive power about how elements will behave and what compounds they'll form, is a quantum mechanical construction. We are already living in a quantum-powered world. We have been for decades. We just don't usually call it that. But there's a new wave of quantum technologies coming. Technologies that don't just exploit quantum mechanics as a background fact about matter. They actively manipulate quantum states to achieve things that are impossible with classical physics. And they take advantage of the very features that seem so strange and paradoxical, superposition and entanglement, as engineering tools. The first is quantum computing. A classical computer processes information in bits. Each bit is either 0 or 1. A quantum computer uses qubits, quantum bits, which by superposition can be 0 and 1 simultaneously. And by entangling qubits together, a quantum computer can process a massive number of possible states at the same time in parallel. For certain types of problems, this gives quantum computers an exponential speed advantage over any classical computer. The most famous example is Shor's algorithm, a quantum algorithm for factoring large numbers. Factoring large numbers is the basis of most modern encryption. The security of your bank account, your messages, your online identity, all rests on the assumption that no computer can factor a 1,000-digit number in a reasonable time. A classical computer would take longer than the age of the universe. A sufficiently powerful quantum computer running Shor's algorithm could do it in hours. This is not a hypothetical threat. Quantum computers are real and getting more powerful every year. The race to build fault-tolerant, large-scale quantum computers is one of the most intense technological competitions in the world right now. Nations and corporations are pouring billions into it, because whoever achieves it first will have the ability to break most of the encryption that underpins the global digital economy. The second major quantum technology is quantum communication, specifically quantum key distribution. This turns the peculiarities of quantum mechanics into an advantage for security. If you use a quantum channel to send a cryptographic key, any attempt by an eavesdropper to intercept it necessarily disturbs the quantum state of the photons carrying the information. And that disturbance is detectable. You can tell if someone is listening. This gives you a communication channel that is provably, physically secure. Not just computationally hard to break, but guaranteed unbreakable by the laws of physics. China has already demonstrated quantum communication between satellites and ground stations over distances of thousands of kilometers. Quantum networks are being tested in cities around the world. The quantum internet, a network of quantum communication channels, is not a science fiction concept. It's a technology being actively developed. The third is quantum sensing. Quantum systems are extraordinarily sensitive to their environment. Tiny fluctuations in magnetic fields, gravitational fields, electric fields, these cause detectable changes in quantum states. Quantum sensors can measure these fields with precision that far exceeds anything achievable classically. Quantum gravimeters can detect tiny variations in the Earth's gravitational field, useful for mapping underground structures, finding oil and minerals, monitoring volcanoes. Quantum clocks, atomic clocks that keep time based on quantum transitions in atoms, are so precise that they lose less than 1 second in billions of years. They're already used in GPS systems and are the world's most precise timekeeping devices. All of these technologies, quantum computers, quantum communication, quantum sensors, are built on the same theoretical foundation that leads to Schrödinger's cat and spooky action at a distance. The same features of quantum mechanics that seem so philosophically troubling, superposition, entanglement, measurement-induced state change, are the very features being harnessed as tools. So when we ask, Does the interpretation matter? Here's a partial answer. Practically, for these technologies, no. The technology works the same whether you believe in many worlds or Copenhagen. The equations are the same. The predictions are the same. The devices function regardless of your philosophical commitment. But deeper answers might matter. There are theoretical suggestions that certain interpretations could lead to new physics that has practical implications. Understanding quantum gravity, the unification of quantum mechanics and general relativity, which remains one of the great unsolved problems of physics, might require us to settle on the right interpretation. And some researchers believe that understanding consciousness, the hardest problem in all of science, might require insights from quantum mechanics. Whether those connections pan out, we don't know. But the stakes are high enough that the question of interpretation is not purely academic. It's about what kind of universe we live in, and understanding that correctly may be the key to the next generation of physics. So what has quantum mechanics actually told us? After all the experiments, all the interpretations, all the Nobel Prizes, all the philosophical arguments, what do we actually know about the nature of reality? Let's start with what the 2022 Nobel Prize definitively established. Bell's inequality is violated. Local realism is false. This is not an interpretation. This is an experimentally proven fact. And it means that at least one of the following two assumptions so fundamental that most people never even think to question them, is wrong. Assumption 1, realism. Physical properties exist with definite values independent of observation. Things have properties whether or not anyone is looking at them. The moon has a definite position when no one is looking at it. Assumption 2, locality. The physical state of one system cannot be instantly affected by events happening at a distant location. Effects have to travel through space. Nothing happens faster than light. Bell's theorem and the subsequent experiments show that you cannot hold both of these assumptions simultaneously. At least one of them is false. Local realism is false. Which one do you give up? That's where the interpretations diverge. Copenhagen says, give up realism. Things don't have definite properties when unobserved. Quantum mechanics describes what we can say about systems when we interact with them, not what those systems really are when we're not looking. Many Worlds says, give up local realism in a specific way. Realism holds, but only relative to a branch. Everything is real, but real within the context of a specific branch of the universal wave function. There's no single objective reality, there are many, all equally real. Bohmian mechanics says, keep realism, particles have definite positions. Give up locality. The guiding wave is non-local. GRW says, keep local realism as much as possible, but accept that collapse is a real physical process that modifies the theory slightly. Cubism says, give up the idea that quantum mechanics is describing reality at all. It's describing the beliefs of agents. The question, what is reality really like, is either unanswerable or meaningless. All of these are philosophically coherent positions. All of them are defended by serious physicists. And all of them make the same experimental predictions. Now here's something that strikes many people as deeply strange when they first encounter it. We have the most successful physical theory in history. We have equations that predict the results of experiments to 10 decimal places or more. We have technology built on those equations that shapes every aspect of modern life. And we don't know what that theory is saying about reality. Is this a crisis? Some physicists think so. They argue that the interpretive ambiguity is a sign that our understanding is incomplete, that there's a deeper theory waiting to be discovered that will make everything clear, the way Newton's laws made clear the mechanism behind Kepler's rules of planetary motion. Others disagree. They argue that the interpretive ambiguity is intrinsic, that there is no fact of the matter about which interpretation is correct, because interpretations are not scientific claims, they're philosophical preferences. The science is in the equations and the predictions. The interpretation is how you choose to understand what those equations mean. And different understanding don't have to agree. But there's a third possibility, one that many physicists find the most uncomfortable of all. Maybe the interpretive ambiguity is telling us something about the nature of knowledge itself. Maybe it's telling us that there are limits to what we can know about the universe from inside the universe. Maybe the question, what is reality really like, independent of any observation, is a question that cannot be answered, not because we're not smart enough, not because our instruments aren't good enough, but because the question itself assumes something that isn't true. The assumption is that there is a fact about what reality is like, independent of any observer waiting to be discovered. The assumption is that the universe has properties that exist regardless of anyone's relationship to them. And quantum mechanics, in every single one of its interpretations, puts pressure on that assumption. Some interpretations dissolve it entirely. Carlo Rovelli, the Italian physicist who developed an interpretation called relational quantum mechanics, puts it this way: there is no absolute universal description of reality. There are only descriptions of reality from particular perspectives, from particular systems interacting with particular other systems. Every system has a perspective, a set of facts about how the world looks from its vantage point. And two systems can have different, mutually inconsistent facts about the same quantum system, and both can be right, from their respective perspectives. In this view, reality is not a collection of objects with properties. Reality is a network of interactions, each of which constitutes a fact from the perspective of the interacting systems. The universe is fundamentally relational. Things don't have properties on their own. They have properties relative to other things. This is a radical idea, and it resonates, even if the connection is not precise, with certain philosophical traditions that have existed for millennia. Buddhist philosophy has long emphasized the relational nature of all phenomena, the idea that nothing exists independently, that all things arise in dependence on other things. The Vedantic tradition speaks of Brahman and Atman, the ultimate ground of reality and the individual self, as being, at the deepest level, the same thing. The boundary between the observer and the observed dissolves. And now quantum mechanics, the most rigorous and precise scientific theory we have, seems to be pointing in a similar direction. Not through mysticism, not through faith, through equations, through experiments, through Nobel Prizes. The observer and the observed are not fully separable. The act of looking changes what's seen. The universe does not have a set of fixed observer-independent properties. It constructs itself, in some sense, through the very process of being observed and interacted with. What does this mean for you sitting here watching this video? It means that you are not a spectator of the universe. You are not floating in an empty void, watching reality play out on a stage somewhere outside you. You are part of the process. Your existence, your observations, your interactions with the world, in some sense, in a sense that quantum mechanics makes precise and testable, contribute to what the universe is. You are not separate from the world. You are the universe doing something. You are a place where the universe is interacting with itself, creating facts, constituting reality through your relationship with everything around you. That is not mysticism. That is physics. Einstein once asked exasperatedly, "Do you really believe the moon isn't there when you're not looking at it?" He was asking it rhetorically. Of course the moon is there. Of course things exist when no one is looking at them. That's what existence means. But quantum mechanics has made this question uncomfortably hard to dismiss. Because at the level of fundamental physics, the answer is not obvious. And the experiments of Clauser, Aspect, and Zeilinger, the experiments that won the 2022 Nobel Prize, have made the question sharper and more urgent than ever. Let's be precise about what is and isn't being said. Quantum mechanics does not say the moon vanishes when you're not looking at it. The moon is made of approximately 10 to the power of 50 atoms. For any macroscopic object of that complexity, quantum superpositions decohere almost instantaneously, on timescales so short they're effectively zero. The interactions between all those atoms and between the moon and the photons hitting it and the gravitational fields it interacts with are so numerous and so constant that quantum coherence cannot be maintained. The moon is effectively always in a definite state. The superposition, if it exists, collapses before you could even blink. So in practice, the moon is there when you're not looking at it. But the question is about principle, about the fundamental nature of physical reality. And at the fundamental level, at the level of individual particles, individual quantum events, the story is different. At that level, the evidence says particles do not have definite properties before measurement. The violation of Bell's inequality rules out any hidden variable theory that tries to restore definiteness by saying, the particle always had these properties, we just didn't know them. The definiteness, the specific outcome, comes into existence at the moment of measurement. Before that, the most accurate thing we can say is that there was a probability distribution, not a definite fact. But here's where it gets even stranger. The moment of measurement, when the wave function collapses, when the outcome becomes definite. Where does that happen? When does it happen? In the Copenhagen interpretation, it happens when the quantum system interacts with a measuring device or an observer. But what counts as an observer? What counts as a measuring device? A particle detector, an atom, a molecule, a bacterium, a rat, a human being, a computer? There's no clear answer. And this vagueness, this gap in the theory, has led some people to speculate that consciousness plays a special role, that the wave function doesn't collapse until a conscious being observes the result. Most physicists find this idea deeply distasteful. Consciousness is poorly understood, poorly defined, and seems like an implausible linchpin for the operation of the physical universe. The idea that the universe was in superposition for the first 9 billion years before conscious beings evolved, and then suddenly started having definite properties, seems absurd. But the alternative, that measurement happens whenever any quantum system interacts with any other quantum system, seems to lead to the many worlds picture. Because if there's no special role for consciousness or macroscopic devices, and if the Schrödinger equation always holds, then everything entangles with everything, and the wave function never collapses, and all outcomes coexist forever. And that's fine from a mathematical standpoint. Many physicists are comfortable with it. But it does mean that there is, in some sense, no single fact about the state of the universe. There are only facts relative to branches. The universe is a vast, constantly proliferating superposition, and each of our experiences is just one branch of that superposition. Now let's come back to Einstein's moon. In many worlds, the moon is always in a definite state, relative to you, in your branch. From your perspective, the moon is always there. But there are other branches where the moon's quantum state is different, and none of those branches is more real than yours. In Copenhagen, the moon's state is only definitively established when a measurement is made. Between measurements, it exists in the quantum state described by its wave function, which is technically not a statement about the moon's definite properties, but about the probabilities of outcomes if measured. In Bohmian mechanics, the moon has a definite position at all times, but it's guided by a non-local wave. The definiteness is restored, but at the cost of non-locality. In cubism, the question, "Is the moon there when no one is looking?" is not a question physics can answer. Physics is about what agents experience when they interact with the world. A moon no one is interacting with is not something physics makes claims about. Every single interpretation gives a different answer to Einstein's question, and we can't currently test which interpretation is right. But here's what we can say, definitively, with the full weight of experimental evidence behind it. The naive picture of reality, a collection of solid, fixed objects with definite properties, existing independently of any observation, interacting only locally, is false. That picture, which feels so obvious, so self-evident, so clearly just common sense, is not correct. Reality, at its deepest level, is something else, something stranger, something we don't have good intuitions about, because we evolved to navigate a world of medium-sized objects moving at slow speeds, and the intuitions we developed are simply not calibrated for the quantum domain. What reality actually is, whether it's a constantly branching wave function, whether it's a web of relationships between systems, whether it's something so alien that our current conceptual frameworks can't capture it, we don't know. And that's not a failure of science. That's the frontier of science. That's where 100 years of the most rigorous intellectual effort in human history has brought us. Not to comfortable certainty, but to the edge of a mystery that goes all the way down. Let's bring all of this back to the 2022 Nobel Prize, because I think the significance of what was proven there doesn't always get the attention it deserves. What Clauser, Aspect and Zeilinger proved is not just a technical result in experimental physics. It is a proof about the structure of reality. It is the most direct, most rigorous, most experimentally grounded answer we have ever obtained to one of the oldest philosophical questions in human history. What is the nature of the world? Here's a way to understand the magnitude of what they proved. Before their experiments, there were two possibilities for how the universe could work. Call them the classical possibility and the quantum possibility. The classical possibility says particles have definite properties at all times, whether or not anyone is measuring them. The correlations between distant entangled particles arise because those particles carried hidden information from the moment they were created, like two gloves separated into two boxes. When you open one box and see the left glove, you instantly know the other box contains the right glove. But that's not magic. The gloves were always left and right. The fact was always there. The quantum possibility says particles do not have definite properties before measurement. The correlations between distant entangled particles are not pre-established by hidden information. They arise at the moment of measurement instantaneously, regardless of distance. Bell's theorem showed that these two possibilities make different predictions. They disagree about the statistics of measurement outcomes in specific experimental configurations. The correlations in the quantum case are stronger, mathematically provably stronger, than anything any version of the classical case can produce. Clauser, Aspect and Zeilinger ran the experiments. They measured the correlations. The results matched the quantum prediction, violating Bell's inequality, ruling out the classical possibility. This is not a subtle effect. In the most careful experiments, the violation of Bell's inequality is not marginal. It's massive. The quantum correlations are wildly stronger than any hidden variable theory could produce. The result is not ambiguous. And what this means is, the world is not classical. The world is not made of fixed things with fixed properties. At the fundamental level, properties come into existence at the moment of interaction. Before that, there is no fact of the matter. This is a proven fact about the universe. Proven with the same rigor as the proof that the Earth orbits the Sun, that DNA is the carrier of genetic information, that the Higgs boson exists. The Nobel Prize is physics' way of saying, this is settled. This is not a hypothesis. This is how nature works. Now, what exactly that means for the nature of reality, which interpretation is correct, what the deep ontological story is, that remains open. The physics is settled. The philosophy is not. But the physics alone is enough to demolish the naive picture. The naive picture, the one that feels like common sense, the one that says the world is made of solid, fixed, independent things, is wrong. And in its place, we have something that no one fully understands, that resists our best intuitions, that has been described as not weird enough to be right by some and too weird to be anything else by others. A universe that behaves as if observation matters. A universe that behaves as if things are deeply connected across any distance. A universe that behaves as if the line between the observer and the observed is not a hard line at all. Whatever that universe is, that is what we live in. So here we are. We started with a magic box, a box that doesn't decide what's inside it until you open it, and we've travelled through atoms and fields and wave functions and interference patterns and cats that are alive and dead and particles that are entangled across galaxies, to arrive at a place that is simultaneously more confusing and more illuminating than where we began. Let's lay out what we know, not what we speculate, not what philosophers have proposed, what physics has established through experiment with confidence. We know that matter is not made of tiny solid balls. It's made of excitations in quantum fields that permeate all of space. We know that particles do not have definite properties before measurement. The double-slit experiment, Heisenberg's uncertainty principle, and a century of quantum experiments all confirm this. We know that local realism is false. The violation of Bell's inequality, proven by 3 Nobel-winning experimental physicists and confirmed by dozens of independent experiments around the world, demonstrates that no theory that combines definite pre-existing properties with local interactions can reproduce what quantum mechanics predicts and what experiments observe. We know that distant entangled particles are correlated in ways that transcend any local explanation. Measuring one instantly tells you something about the other, regardless of the distance between them. We know that the classical picture of the universe, deterministic, local, with particles having fixed properties independent of observation, is not how the universe actually works. And we don't know, we genuinely, honestly, despite a century of effort, do not know what quantum mechanics is saying reality actually is at the deepest level. We have several coherent interpretations. We can't test between them. The debate continues. What does that leave us with? It leaves us with this. The universe is not a collection of things. The universe is not a stage on which events happen. The universe is not sitting out there, fully formed and waiting to be discovered. The universe is a process, a constant, unfolding, self-creating process. Something is happening. Something is always happening. At every scale, from the quantum fluctuations in the vacuum of empty space to the spiral arms of galaxies. And that happening, that process, is not separate from the beings who observe it, measure it, experience it. You are not watching the universe from the outside. There is no outside. You are part of the process. You are a place where the universe is doing something, interacting with itself, creating facts, generating experience. Your act of observation, the light from your surroundings entering your eyes, the photons colliding with the rhodopsin molecules in your retina, triggering a cascade of quantum mechanical events that ultimately gives rise to the experience of seeing, is not passively recording a pre-existing reality. In some sense, that quantum mechanics makes precise and that the Nobel Prize has validated, your interaction with the world is part of what the world is. That is not a mystical statement. That is a physics statement. And if it sounds philosophical, it's because physics, at its deepest level, has become philosophical. The two are not separate. At the frontier of what we know, science and philosophy converge on the same questions. What exists? What is knowledge? What is the relationship between the observer and the observed? And for the first time in history, we have experimental data, Nobel Prize-winning experimental data that puts genuine constraints on the answers to those questions. Not all answers are possible. Local realism is ruled out. Some things we thought were obvious, that the moon is definitely there when no one looks, that particles carry hidden properties, that the universe is made of separate, independent things, are not simply common sense anymore. They are claims that have been tested and found to be false. The universe is stranger than we thought, stranger than we feel comfortable with, stranger than our evolution prepared us to understand. But it's also more interconnected, more participatory, more alive with relationship than the cold, clockwork, deterministic machine that classical physics imagined. And the fact that we can probe it, that we can design experiments clever enough to test Bell's inequality, that we can entangle photons and send them across cities, that we can use the weirdness of quantum mechanics to build computers and secure communications. That fact is itself something extraordinary. The universe has in us produced something that can ask questions about its own nature. And it has in quantum mechanics started to give us answers. Strange, unsettling, beautiful answers that we are still, after 100 years, learning how to hear. We don't fully understand what reality is, but we know it's real. We know it's here. We know it's doing something, and we know that whatever it is, we're not separate from it. We're part of what it's doing, and maybe, just maybe, that's enough. If you made it this far, thank you. Genuinely. This is the kind of content I pour everything into, and knowing you're here for it means everything. If this opened something up for you, if it left you a little unsettled, a little more curious, a little more in awe of what exists, then drop it in the comments. I want to hear where your mind went, and if you're not subscribed yet, what are you doing? Hit subscribe, turn on the bell, and I will see you in the next one. We mentioned the double slit experiment earlier, but I want to spend more time here, because this one experiment contains almost everything that is strange about quantum mechanics, compressed into a single setup. Richard Feynman, one of the greatest physicists of the 20th century, once said that the double slit experiment has in it the heart of quantum mechanics. In reality, it contains the only mystery. He believed that if you truly understood what the double slit experiment was showing you, you understood everything there was to understand about quantum mechanics. So let's really look at it. The setup is simple. You have a source that emits particles. Let's use electrons because they're easy to think about. You have a barrier with two narrow slits cut into it, and behind the barrier you have a detector screen. Imagine a wall that lights up wherever an electron hits it, leaving a mark. You fire electrons, one at a time, and watch where they land. Now, before I tell you what happens, let me tell you what you'd expect to happen, based on classical physics, if electrons were tiny balls. Tiny, solid, well-defined objects with definite trajectories. If you fire a tiny ball at a barrier with two slits, the ball goes through one slit or the other. It can't go through both. After passing through, it continues in roughly the same direction and lands somewhere on the detector screen. If you fire many balls, you build up two clusters of impacts on the screen, one cluster behind each slit, two piles. That's what classical balls do. And if electrons were just tiny balls, that's what you'd expect. Two piles. One for slit 1, one for slit 2. That's not what happens. When you fire electrons at the double slit, with both slits open and without watching which slit each electron goes through, you get an interference pattern. You get a series of alternating bright and dark bands on the screen. Many electrons land in some places. No electrons land in other places. And the pattern of which places have electrons and which don't is the pattern that you'd get if you were sending waves through the slits, not particles. When a wave goes through two slits, it fans out from each slit, and the two fan-shaped waves overlap with each other. Where the peaks of both waves coincide, they add up. That's a bright band, where many particles land. Where the peak of one wave coincides with the trough of the other, they cancel out. That's a dark band, where no particles land. This is called interference, and it's the hallmark of wave behavior. Electrons produce this interference pattern, which means electrons are behaving like waves. But here's the paradox. Electrons are also clearly particles. When one arrives at the detector screen, it arrives at a single point. It produces a single tiny dot, not a smeared out wave. As you keep firing electrons, the dots accumulate, and the pattern that they accumulate into is the interference pattern. Each individual electron lands in one place, like a particle, but where it lands is governed by the interference pattern, like a wave. Every electron is somehow both, simultaneously. Now it gets stranger still. What happens if you fire electrons one at a time, with a long time between each one? Surely if you're only sending one electron at a time, there's nothing for it to interfere with. A wave can only interfere with itself if there are two waves to overlap. But if you fire electrons one at a time, each one goes through alone. There's no other electron to interfere with. You still get the interference pattern. Somehow, each individual electron, fired alone, with no other electrons present, with nothing to interfere with, still produces an interference pattern across the screen. The only possible explanation is that each individual electron is in some sense going through both slits simultaneously, that a single electron exists as a wave that passes through both slits at once, interferes with itself, and then collapses to a point when it hits the screen. A single electron, going through two slits at the same time. This is superposition made viscerally visible. The electron is in a superposition of went through slit 1 and went through slit 2. It takes both paths simultaneously. And the interference between those two paths determines the probability of where it lands. But now, watch what happens when you add a detector. You put a tiny detector at one of the slits, something that will register which slit each electron passes through. You want to catch the electron in the act of going through slit 1 or slit 2. You want to know which path it took. The interference pattern disappears. Completely. The moment you gather information about which slit the electron went through, the pattern on the screen changes from the interference pattern to the two piles classical pattern. The electron now behaves like a classical particle, going through one slit or the other and landing in the pattern appropriate for particles, not waves. This is wave function collapse made visible. The moment you measure which path the electron took, the moment the which path information is encoded anywhere in the physical world, the electron's wave function collapses from the superposition to a definite path. The interference, which required the superposition, disappears. Now here's what makes this even more disturbing. You don't have to actually look at the detector results. You just have to have a detector that could in principle tell you the which path information. Even if you never check the detector, even if no human ever sees the result, the interference pattern disappears. The mere fact that the which path information is physically encoded, that it exists somewhere in the world, in the state of some detector atom, is enough to destroy the interference. And conversely, if you set up the detector but then erase the information before it can be read, if you somehow ensure that the witch path information is destroyed and can never be retrieved, the interference pattern comes back. This is called the quantum eraser experiment, and it has been performed, and it works exactly as described. The interference pattern depends not on whether you look, but on whether the information exists in the world. The universe seems to care about information, about what's knowable, about what records have been created, not just about what conscious beings happen to check. This is deeply, profoundly mysterious, and it suggests that information, not just matter, not just energy, but information, may be fundamental to reality in a way we're only beginning to understand. John Archibald Wheeler, one of the giants of 20th century physics, the man who coined the term black hole, spent the last decades of his life developing what he called the it from bit hypothesis. His idea was that information is more fundamental than matter or energy, that physical reality, the it, arises from information, the bit, that at the deepest level, the universe is made of information, that asking, does it exist, is the same as asking, has it been registered, recorded, noted? Most physicists today think Wheeler's idea was too extreme, or at least too early, but the quantum eraser, the witch path experiment, and decades of information theoretic work in quantum physics have made it impossible to dismiss information as a mere bookkeeping tool. Information does something. Information matters. Information, in some deep sense, is part of what the universe is made of. One of the most common questions people ask when they first encounter quantum mechanics is, if all this strange quantum behavior is real, why don't we see it? Why doesn't a chair go into superposition? Why doesn't a coffee cup interfere with itself? Why does the quantum weirdness seem to disappear at the scale of everyday objects? The answer is decoherence, and it's one of the most important concepts in modern quantum physics. Here's the core idea. When a quantum system is perfectly isolated from its environment, when it doesn't interact with anything, when no information about its state leaks out into the surrounding world, it can maintain a quantum superposition indefinitely. The wave function evolves according to the Schrödinger equation, and the superposition is perfectly preserved. But here's the thing. In the real world, nothing is perfectly isolated. Every system is constantly interacting with its environment. An electron in a superposition is interacting with air molecules, with photons bouncing around the room, with the electromagnetic field. A Schrödinger's cat is interacting with the atoms of the box, the air inside, the photons and phonons, and everything else. When a quantum system interacts with its environment, something happens. The system becomes entangled with the environment. The state of the system and the state of the environment become correlated. The system is no longer in a superposition on its own. It's now part of a joint quantum state that includes the environment. And here's the crucial point. The environment is enormous. It contains an astronomical number of particles. When the quantum system entangles with those particles, the quantum information, the information about the superposition, gets spread out across all of them. It becomes encoded in the correlations between the system and trillions of environmental particles. This spreading of quantum information into the environment is decoherence. And once it happens, the quantum interference effects, the thing that makes superposition physically visible, as in the double-slit experiment, are, for all practical purposes, gone. The quantum system appears to be in a classical mixture of states rather than a quantum superposition. Why? Because to observe interference, you'd have to measure not just the system, but all of the environmental particles it's become entangled with, simultaneously in a coherent way. And that is experimentally impossible for any macroscopic environment. There are simply too many particles spread out too widely for us to ever control them all well enough to see the interference. So from our perspective, from the perspective of anyone observing the system without also tracking every environmental particle, the system looks classical. The superposition is there, in principle, in the full quantum state of the system plus environment. But it's hidden from any practical observation. It's been diluted beyond recovery. This is why chairs don't go into superposition. They do, in principle. Every quantum mechanical process that applies to electrons also applies to chairs, which are made of electrons. But chairs interact with their environment, with air, with photons, with the floor, at a rate so fast and so thorough that any superposition decoheres in an unimaginably short time. The decoherence time for a macroscopic object in ordinary conditions is something like 10 to the minus 40 seconds. Much, much shorter than any measurement we could ever make. For microscopic quantum systems, individual electrons, photons, atoms, decoherence is much slower. If you cool things down, remove them from the environment, eliminate electromagnetic disturbances, you can maintain quantum coherence long enough to observe and use it. This is essentially what quantum computers do. They work desperately hard to keep qubits isolated from their environment because any interaction causes decoherence and destroys the quantum computation. Now, does decoherence solve the measurement problem? Does it explain why we see one outcome rather than another when we make a measurement? The answer is not fully. Decoherence explains why quantum superpositions become undetectable at the macro scale. It explains why the off-diagonal elements of the density matrix, the mathematical terms that represent interference, become vanishingly small once the system entangles with the environment. In this sense, it explains why the world looks classical, but it doesn't explain why a particular outcome occurs. The full quantum state, system plus environment, plus measuring device, plus observer, is still in a superposition. The superposition is just enormously entangled. The interference is inaccessible, but it hasn't gone away. In the Schrödinger equation's perspective, all outcomes are still there, encoded in different parts of the entangled state. So decoherence is a crucial part of the story. It explains the practical transition from quantum to classical, but it leaves the fundamental question: what actually happens when a measurement is made? Unanswered. That question still belongs to the interpretations, and the interpretations still disagree. What decoherence does tell us very clearly is this: the quantum and classical worlds are not separate domains. There is no hard boundary between them. Classical behavior is what quantum mechanics looks like when decoherence has done its work. The solid classical world we experience is the quantum world, seen through the lens of unavoidable environmental entanglement. Everything is quantum, all the way up. Albert Einstein is often remembered, in the context of quantum mechanics, as the man who refused to accept it. The man who said, "God does not play dice." The man who was eventually proven wrong by Bell's experiments. The man who fought the revolution in physics and lost. That picture is not wrong, but it's incomplete. And the complete picture is much more interesting. First, Einstein's contributions to quantum mechanics were enormous. Arguably, without Einstein, quantum mechanics would have taken much longer to develop. His 1905 paper on the photoelectric effect, for which he won the Nobel Prize, not for relativity, introduced the concept of the photon, the quantum of light. This was the paper that first forced physicists to take seriously the idea that light, which everyone knew was a wave, was somehow also a particle. This was one of the founding acts of quantum mechanics, and Einstein's 1917 paper on stimulated emission, the process by which an excited atom can be triggered to release a photon by an incoming photon, laid the theoretical groundwork for the laser. Every laser that has ever been built, every CD player, every barcode scanner, every laser pointer, owes its existence in part to that 1917 Einstein paper. So Einstein wasn't someone who didn't understand quantum mechanics. He was someone who understood it extremely well and who found it deeply troubling for specific, carefully articulated reasons. What were those reasons? Einstein's core complaint was about the completeness of quantum mechanics. He accepted that quantum mechanics worked, that it made correct predictions. What he denied was that it was a complete description of physical reality. He believed there was more to the world than what quantum mechanics captured, that there were hidden facts, hidden variables, underlying the quantum description that, if we could access them, would restore the determinism and locality he felt the universe must have. His argument wasn't aesthetic. It wasn't just that he personally preferred a deterministic universe. He had a specific philosophical commitment that physics should describe an objective reality, independent of observers, that the moon should have a definite position whether or not anyone is looking at it, that two particles separated by light years should not be able to influence each other instantaneously. These seem like eminently reasonable things to ask of a physical theory, and Einstein's frustration was that quantum mechanics seemed to violate both of them. That was his objection to the Copenhagen interpretation, not that it was wrong in its predictions, but that it had given up on describing objective reality, that it was telling physicists, just use the equations, don't ask what they mean. Einstein thought that was a failure of nerve. He thought that one day a deeper theory would be found that restored objectivity and locality, and that quantum mechanics would be revealed as an approximation to that deeper theory, useful but incomplete, the way Newtonian mechanics turned out to be an approximation to relativistic mechanics. He was wrong about the hidden variables. Bell's theorem and the experiments that followed closed that door. You cannot have a theory that is both local, effects don't travel faster than light, and realistic, particles have definite hidden properties, and still reproduce the quantum predictions. Einstein wanted both. You can't have both. But Einstein was right about non-locality being strange. He was right that quantum entanglement represents a genuine departure from the kind of local, separable view of the world that classical physics assumed. He was right that this needed to be taken seriously, not brushed aside. The EPR paper, the paper he wrote with Podolsky and Rosen that first articulated the entanglement puzzle, was not wrong. It correctly identified a genuine weirdness in quantum mechanics. It just drew the wrong conclusion. Instead of concluding that quantum mechanics was incomplete, the right conclusion was that the world is non-local. Einstein was also right about something deeper and more philosophical. He was right that the question of what physics is trying to describe matters. That shut up and calculate is not a satisfying answer to what is reality. He was right that physicists should grapple with the interpretive question, not dismiss it. And the century of argument that his objections sparked, the Bell inequalities, the entanglement experiments, the proliferation of interpretations, the quantum information revolution, all of that is in part a tribute to the seriousness with which he took the question. He asked the right question. He got the wrong answer. But asking the right question in physics is often harder than finding the right answer. And Einstein, in his dogged, passionate insistence that quantum mechanics was not saying what its practitioners thought it was saying, pushed the field to be more honest, more careful, and ultimately more profound about what it was doing. He was the gadfly of quantum mechanics. And gadflies, even when they lose the argument, sometimes move things forward more than those who win it. We are living in what physicists are calling the second quantum revolution. The first quantum revolution, which took place from roughly 1900 to 1930, was the discovery of quantum mechanics itself. the development of the theoretical framework, the recognition that the subatomic world plays by different rules, and the first wave of technology that sprang from that understanding, transistors, lasers, LEDs, MRI machines, the foundation of the modern digital world. The second quantum revolution is happening right now. It's about taking quantum mechanics beyond passive exploitation, beyond just using the fact that matter obeys quantum laws, and into active manipulation of quantum states, deliberately creating and controlling superpositions, entanglement, and quantum coherence, and using them as engineering resources. This is the era of quantum computing, quantum communication, and quantum sensing that we discussed earlier. But the implications go even further. Consider quantum simulation. One of the problems with understanding complex quantum systems, like the behavior of electrons in high-temperature superconductors, or the folding of proteins, or the dynamics of chemical reactions, is that classical computers can't simulate them efficiently. The quantum state of even a modest-sized system has an astronomical number of parameters. A system of 50 entangled qubits has more states than there are atoms in the visible universe. Classical computers can't handle that. But a quantum simulator, a carefully controlled quantum system in the laboratory, can simulate other quantum systems naturally. You set up the simulator to have the same Hamiltonian, the same fundamental interaction rules as the system you want to understand. And then you let it run. You let quantum mechanics do the computation for you, because quantum mechanics can naturally represent and evolve all those exponentially many states simultaneously. This could be revolutionary for chemistry, for materials science, for drug discovery. Understanding exactly how a drug molecule interacts with a protein target requires quantum mechanical calculations of enormous complexity. Classical computers approximate. Quantum simulators could do it exactly. The prospect of designing drugs molecule by molecule with perfect quantum mechanical accuracy could transform medicine. It could also be revolutionary for our understanding of the universe itself. Quantum gravity, the quantum mechanical description of space and time, is one of the deepest unsolved problems in physics. String theory, loop quantum gravity, causal set theory, and other approaches are all attempts to bridge quantum mechanics and general relativity. We don't know which approach is right, partly because the phenomena involved are at energy scales so high that we can't probe them directly with particle accelerators. But some researchers believe that certain aspects of quantum gravity could leave observable traces at lower energies, in the structure of quantum field theories, in the behavior of black holes, in the early universe. And quantum computers and quantum simulators might be able to model these systems well enough to give us indirect evidence for one approach or another. There's also the extraordinarily speculative, but increasingly discussed question of consciousness. The relationship between quantum mechanics and consciousness has a long, complicated, contentious history. In the early days of quantum mechanics, some physicists, including John von Neumann and Eugene Wigner, suggested that consciousness might play a special role in wave function collapse. That the collapse didn't happen until a conscious observer became aware of the measurement result. Most physicists today reject this idea. Decoherence explains the classical appearance of the world without invoking consciousness. And putting consciousness inside physical theory as a fundamental ingredient creates as many problems as it solves. But there's a different, more recent line of thinking. Roger Penrose, the Nobel Prize-winning mathematical physicist, and Stuart Hameroff, an anesthesiologist, have proposed a theory called orchestrated objective reduction, or ORC-OR. They argue that quantum processes in the brain, specifically quantum computations in structures inside neurons called microtubules, are the physical basis of conscious experience. That consciousness isn't just correlated with neural activity, but actually arises from quantum mechanical processes within neurons. This theory is extremely controversial. Most neuroscientists think it's wrong. The brain is warm and wet, terrible conditions for maintaining quantum coherence, and there's no clear evidence that quantum effects in microtubules play any functional role in cognition. But it's not ruled out, and some recent experiments have found surprisingly long-lasting quantum coherence effects in biological systems, in photosynthesis, in bird navigation, in the sense of smell. Biology seems to exploit quantum mechanics more than we expected. Whether it does so in the brain, and whether that has anything to do with consciousness, remains deeply unclear. The honest position is, we don't know. But the fact that we're even asking the question, the fact that the relationship between quantum mechanics, information, and consciousness is considered a serious research area, even if a controversial one, is a testament to how far quantum mechanics has pushed us beyond the comfortable certainties of classical physics. And there's one more thing to say about the quantum future, about the long game. Quantum mechanics is about 100 years old. In that time, it has given us the transistor, the laser, MRI, the entire digital world. It has given us the most precise tests of physical theory in history. It has given us a revolution in our understanding of reality. We are now apparently at the start of the second quantum revolution. And if the first quantum revolution produced the digital world in roughly 50 years, from the invention of the transistor in 1947 to the World Wide Web in 1991, what will the second one produce in the next 50? We genuinely don't know, and that not knowing, that open horizon, is one of the most exciting things about being alive in this particular century. The magic box is still open, we're still looking inside, and we're still surprised by what we find. There's one more dimension of quantum strangeness that doesn't get enough attention in popular discussions, and it concerns something so fundamental that we usually take it entirely for granted: time. In our everyday experience, time has a direction. The past is fixed and the future is open. Causes precede effects. You can remember yesterday, but not tomorrow. The arrow of time runs one way and only one way. But in quantum mechanics, and even more dramatically in quantum field theory, time is strange. And the things that quantum mechanics says about time are connected in deep ways to the things it says about reality. At the level of fundamental physics, the laws of nature are almost completely time-symmetric. The fundamental equations, the Schrödinger equation, the laws of quantum electrodynamics, the standard model of particle physics, work equally well in either time direction. If you made a movie of a few particles interacting at the quantum level and played it backward, the backward movie would be indistinguishable from a valid physical process. The laws don't distinguish between past and future. So where does the arrow of time come from? Why does the future feel so different from the past if the underlying laws don't distinguish them? This is the arrow of time problem, and it's one of the deep unsolved problems in physics. The standard answer is thermodynamics. In systems with many particles, there's an overwhelming probability that things evolve toward higher entropy, toward more disordered states. And entropy defines the arrow of time. We remember the past and not the future because the past has lower entropy. But this thermodynamic answer is not fully satisfying. It pushes the question back: why was the past low entropy? Why was the universe in an extraordinarily ordered state at the Big Bang? The answer seems to require special initial conditions, a fine-tuned starting point with very low entropy. And we don't have a deep explanation for why the universe started that way. Now here's where quantum mechanics makes things even more interesting. In quantum mechanics, as we've seen, the act of measurement is not time-symmetric. The collapse of the wave function, if it's real, is a one-way process. You start with a superposition, you make a measurement, you get a definite outcome, and you cannot run it backward. The superposition is gone. Some physicists have argued that this measurement irreversibility is connected to the thermodynamic arrow of time, that the collapse of the wave function is fundamentally a thermodynamic process, an entropy-increasing process, and that the two arrows of time are actually the same arrow in disguise. Others point to entanglement. When a quantum system becomes entangled with the environment, when decoherence occurs, that too is an irreversible process in practice. The quantum information spreads out into the environment and can never be fully recovered. This spreading of entanglement across an ever-growing number of environmental particles could be the quantum mechanical origin of the thermodynamic arrow of time. And then there's the delayed choice experiment. John Wheeler proposed a version of the double-slit experiment in which the choice of whether to observe which path information is made after the particle has already passed through the slits. After the particle, as a wave, has already gone through both slits and started to form the interference pattern. And then, after that, you decide to measure which slit it actually went through. What happens? The interference pattern disappears, as if the particle, retroactively, decided to have gone through one slit rather than both, at the moment you retroactively made the choice to observe. This is deeply uncomfortable. It suggests that the choice you make now, after the particle has already done its thing, can affect what the particle did in the past. That, in some sense, the past is not fixed until the information is recorded. Wheeler called this the participatory universe, the idea that the present can reach back and shape the past, at least at the quantum level, that the universe is not a fixed pre-existing structure that we're discovering, that it's something that is, in some sense, being constructed by observation. Delayed choice experiments have been performed. They work as described. The results are exactly what quantum mechanics predicts. And what quantum mechanics predicts seems to say that the past, at the quantum level, is not fixed until information about it is recorded. Is this real retrocausality, real causation going backward in time? Or is it a subtle illusion created by how we think about the quantum wave function? Physicists disagree, but the experimental facts are real. The quantum world does not respect our intuition that the past is fixed and the future is open. Time, at the quantum level, is at least as strange as space, and possibly stranger. And all of this, the time-symmetric fundamental laws, the thermodynamic arrow, the delayed choice experiment, the role of information and entropy in measurement, points toward a vision of the universe in which time is not a background structure that events happen in, but something that emerges from the quantum processes themselves, something that arises from the statistics of entanglement and entropy, something that is, at the deepest level, not as fundamental as we thought. This connects to one of the most radical current approaches in theoretical physics, the idea that space and time are not fundamental, that they are emergent, that they arise from something more fundamental, possibly quantum entanglement itself. There are serious theoretical results suggesting that the geometry of space, the fact that things have spatial locations and distances between them, can be derived from the pattern of entanglement in a quantum system. In other words, space is made of entanglement. The spatial distances between things reflect the degree to which they're entangled. And time, the arrow of time, the sense in which the future is different from the past, emerges from the thermodynamics of quantum information. If this is right, then the deepest level of reality has no space, no time, just quantum information, just correlations, just entanglement. And space and time are structures that emerge from it, the way temperature emerges from the motion of molecules, or the way the surface of water emerges from the behavior of individual water molecules. This is the frontier. This is where physics is going, and it is staggeringly, beautifully strange. The universe we live in, the one with stars and planets, and cats and Nobel Prizes, and people watching YouTube videos about quantum mechanics, may be a kind of projection of something more fundamental, a high-level description that emerges from a lower level that doesn't look anything like our familiar world, a world without space, a world without time, a world made entirely of information, of relationships, of the quantum mechanical correlations between things. And the question that quantum mechanics has been asking us for a century, what is reality, is not a question that's getting easier. It's getting harder and deeper and stranger the closer we look. And that's exactly where it should be. That's what the frontier of knowledge looks like.